Well, hello again everybody. Well, as I'm sure that you'll know, it's quite a while since I last made a video, and some of you have got in contact with me just to see if everything is okay. And I'm glad to report that yes, everything's fine. Unfortunately, just been exceptionally busy with work. I've actually been doing an awful lot of electronics at work and software, and really just haven't had any time. And having worked all day with electronics, software and computers, at home I decided to have a little bit of a digital online detox, where really I've just been going out for walks, taking it easy and enjoying the summer. But as you can see, I'm back. You can see on the bench today we've got a range of test equipment, and I actually picked all this equipment up as a job lot from the British Vintage Wireless Society from one of their rallies, and it was a job lot. It all just came in a cardboard box, various junk, and I think all these things together, I actually only paid about £7 for them because at the end of the day nobody else wanted them but me. Got to admit, I didn't really want them either, but I just couldn't walk away from them for £7. So starting off at the left hand side, you can see we've got this Philby 1503. Now I'm not exactly sure what the date of these are from. I'm guessing maybe late 80s or 90s. I don't think they're a particularly outstanding voltmeter. I didn't particularly want to buy it, but it came in the job lot. But I did actually think it was quite interesting that on the back of it, it does have this Motorola sticker. So it obviously came from something radio related anyway. And I'm also quite a fan of Philby equipment. And we've got the manufacturer's label on the back here, made in England by the Philby Electronics Limited Company, New Road, St Ives, and they were in Cambridge. Next to our voltmeter, we've got this Taylor model 65B, and it's an all-wave signal generator. And this covers a frequency range between 100 kHz and 23 megacycles, and it does that in 5 steps. And roughly these were manufactured between about 1942 and 1948, and they were manufactured by the Taylor Electrical Instruments Company, and they were based in Dover, England. And out of the job lot of test gear, it was really only this Taylor signal generator that I was particularly interested in because I quite like the styling of it, and it does seem to be fairly intact. Although I can see that it had some modernisation done because it's got modern BNC connectors on it. But apart from that, all the controls look to be in fairly original condition. They have this very nice frequency adjustment control here, and it's got this lovely surrounding bright chrome bezel. I really think they're quite an attractive piece of test gear, and they can actually still work quite well. So hopefully we might be able to put this to use in the workshop if we can get it working. And next to our Taylor signal generator, you can see we've got another piece of vintage equipment in the form of a test bridge, and this is also made by the Avo company, and these were manufactured between 1936 and approximately 1947, and by all accounts, reading some of the literature online, they were actually quite good performers. So what you can use these for is you can actually measure the resistance of resistors, but more importantly what these were really used for is for actually checking out the value of capacitors, because of course we're all spoilt with these modern Chinese component analyzers now, where you just clip a capacitor onto them and it reads out the capacitance. Well, it wasn't so easy back in the day. You had to use a piece of equipment like this, and I think these were particularly favoured because of their small size, and they are quite portable. Well, I say that it's portable, the equipment does actually require to be plugged into a 230 or a 240 volt supply, so you do need mains power, but this would still be considered as a piece of portable equipment. Now they could actually do a few other things as well. They could actually measure the goodness of the capacitor, in that they could also measure power factor, and I think that they could also maybe give some indication of leakage via this little neon bulb that's on the side here. So this might be quite interesting to take a look at some point in the future and see if we can get it going. And the final part of our vintage test gear score consists of this advanced RMS voltmeter, and I think this is a model number 77A for those playing along at home, and it was manufactured around 1960 by the Advanced company. Now of course the Advanced company were also very famous for making signal generators, so perhaps that's one of the reasons why I chose to sit it on top of this Taylor signal generator here. Now I'm really not sure if this is going to be any use or not. I mean, it will actually go down to, I think these go down to about 1 millivolt, so that could be quite useful. So yeah, quite a low voltage there. but the readout is only for RMS faults. And taking a closer look at this very nice analog meter, we can see that it's also got a dB scale, which of course can be quite useful. And I can see here that we've got 1 milliwatt here into 600 ohms, so this would suggest that it was maybe for audio or maybe some form of telephony use. Have we got a frequency response there? Okay, it says 15 cycles to 4.5 megacycles, so a relatively high frequency range for a piece of equipment of this age. Now inside here they did actually manage to cram 6 valves, so we've got 4 times 6AK5S's, we've got an ECF80 and we've also got a 6AQ5 valve. Now I haven't actually decided if we're going to restore this or not yet. I mean, the overall meter is in really good condition, so it would be quite nice, but I'm not sure how much use it would get. And I've also got better vacuum tube voltmeters manufactured by the likes of Marconi, which are probably better and will do a range of AC and DC, which is perhaps just a little bit more useful than this one. But it isn't just in such lovely condition, isn't it? Maybe we should resurrect it. Let me know, leave it in the comments. As you can see, I've tidied away some of the other test gear because I think we'll look at some of those items on another day, but I am quite interested just to do a quick resurrection video on this Taylor Model 65B signal generator. Now, looking at the overall condition of it, it looks like it has been stored at some point in a damp shed, as a lot of this equipment has, unfortunately, because I can see that the plating on here, it's very heavily pitted with rust. That always does concern me when you find rusty piece of equipment, because you'll find a signal generator like this is actually packed with inductors. It will have a coil box with some inductors in there. They're probably wound on some quite fine wire. Now, if this equipment has been exposed for damp conditions for quite a long period of time, the most common fault that you get is that wire, the wire on the inductors goes green and it corrodes away, and it can be quite difficult to salvage that unless you actually know how the original inductors were wound and values, etc. So it may or may not be worth resurrecting, but apart from the light surface rust, it doesn't really look in too bad a condition. Let's just turn it round, and of course it's, well, nothing exciting at all on the back there, so yeah, let's turn it back round. It's constructed from a mild steel box, and the front of it here has got that crackle paint finish, but I'm sure you'll agree what really grabs the eye is this really splendid frequency adjustment dial. Isn't that just wonderful? And what you've got consists of, you see we've got this double needle, so the top needle here, this is a kilocycles range, so that's the lower frequency end of the signal generator, and then the bottom needle pointer here works on the high frequency end, and we haven't got any of those megahertz. Of course we've got megacycles, which is pretty cool, isn't it? But I just really do like the way that these are constructed, and as you can probably imagine, we've got a lovely smooth moving frequency adjustment knob here. You can also see, just looking at it, looks like mains on and off. It looks like we've got internal modulation of 400 cycles, so this will obviously modulate the carrier wave, or we've also got external modulation, or CW, constant wave. Now, it does say that this produces an audio output, so I'm not sure about that, because the frequency range, according to the instruction manual, says that it starts at 100 kilohertz, which obviously would be outside of the audio range. Maybe that's a modulated output, I'm not exactly sure. We've got a modern BNC connector here and an RF BNC connector labelled up here. Obviously this has been replaced. These would have been, I think, little plug-in connectors on a Bakelite panel. I think maybe all the knobs are original. Certainly they've got some of that emulsion paint on them, which is common to all vintage equipment. Looks like we've got the main frequency control here, and that goes from, on one range it goes from 100 kilocycles all the way to 23 megacycles. And we've got two RF output controls here, which I'm guessing are just basically RF attenuators. So you've got a coarse control here on the bottom, which goes in ranges from ×1 to ×10,000, and then you've got a fine RF adjustment here. And I can also see at the right hand side of the instrument here we've got various voltage selections. So what does this go from? It goes from 110 volts to 210, and then finally we've got a 240 volt tapping. So let's return this little thumb screw here to the 240 volt tapping. Before that we go any further today, I think really we need to take this out of its cover and have a look inside for any electrical problems. We can see that at some point in the past there has been some electrical work done on this, because we've got a modern mains flex. So somebody's been here in the not too distant past, but of course we don't know what the quality is. We don't even know if there's any valves in here, or if the output transformer or the modulation transformer, we don't know if any of that's burnt out. So we need to just check all those inductors and take a look inside. So let's pull the cover off and take a closer look. And I think we'll start a little project box for this signal generator, because obviously that makes it easier to actually lose all the screws in one go, so we'll do that. Quite a lot of screws here, so I'll tell you what, I'll bring you back when I'm done. It's got a definitely musty smell. Does anything look burnt? Looking good so far. I think that before we make a close-up inspection of our signal generator here, I'm going to just go ahead, I'm going to remove the mains plug, because once I've done that I can actually remove this mains lead, which is actually wired through the case. I can take the case off the bench then and just save some room. But as soon as we're here, let's have a quick impromptu game of plug bingo. So anybody get any ideas? I'm going to go for 3 amps. Place your bets now, here we go. Oh, fail. Of course, 13 amp fuse with a 3 amp mains flex. That's why we always check the plug and make sure that we've got a suitable fuse in here, which really wants to be something like about a 1 amp fuse. As small as you can put in it, that's what we need here. But it is a relatively modern plug, because we can see that it has got the plastic insulators on it. But yeah, I think I'll probably go ahead and replace it anyway, because it doesn't look great, does it? Well, as you can see, our Taylor 65B, it came out of its cabinet quicker than a Barnsley girl comes out of her underwear on a Friday night. So we can see we've got an incoming mains cable here. This has clearly been replaced at some point in the past, because the original lead, much like the internal wiring, it would have been a cloth covered lead. So this has been replaced, and a lot of the wiring does appear quite crude, especially the way that this actual mains tag strip here, it's directly soldered onto the back of a pot, which does seem, I don't know, just a little bit how you're doing. And then we've got the earth conductor, which is soldered to a tag strip on this metal can. Now inside this metal can we've basically got an RFI pi filter, consists of a couple of inductors and what I think are some silver mica capacitors. In fact, we could probably just remove this and take a quick look inside, couldn't we? So you can see we've got 4 capacitors here. I'm not certain, but given that the value and the size and shape of these, I think these are probably silver mica capacitors. And we've also got a bobbin here which has got 2 inductors wound onto it. Now the purpose of this little doobry here, this is an RFI filter. What it will do is it actually stops any high frequency, any RF getting out onto our mains lead and being transmitted through our workshop. But I suspect it also serves the purpose of actually stopping mains-borne interference getting onto the signal generator and maybe cross-modulating with some of the internals and actually producing some odd outputs. So I think that this filter, this pi filter, probably serves 2 functions. Now if you look at the capacitor arrangement here, you'll actually see that each of these capacitors is connected effectively between neutral and earth and live and earth. Now normally when you've got that arrangement you would want to replace these capacitors with an appropriate safety rated capacitor, which would actually be a Y rated capacitor. Now I don't have anything suitable in stock. I think these silver mica capacitors are generally relatively reliable, so I'm just going to go ahead and pretend I haven't seen that and put the lid back on. And from our RFI, our radio frequency interference filter, the actual mains wiring comes onto the back of this selector switch here, which actually switches the power on and off to the transformer. So the transformer here, it's actually got selectable tap-ins from anywhere between 110 and 240 volts, And of course this transformer is going to be providing a step down transformer to actually power up the valve filaments here, the heaters to our valves, and it's also going to be providing the high voltage supply. Now of course things like transformers can be quite difficult or expensive to replace in vintage valve equipment, so pretty early on what we're actually going to do is we're going to test this transformer, we're going to put some power on it and make sure that this works, because if the transformer doesn't work there really isn't any point in going much further, is there? So we come out of the transformer and we go here to a full wave rectifier valve, which in this case is a 6x5. This is quite an early valve, comes from around 1936, something like that, and it kind of really does date the design. In fact the other valves here, we've got two triode valves. So we've got a triode valve here, which is, this valve is actually used to produce a modulation tone, and then we've actually got the RF oscillator valve here adjacent to the actual range selection switch. So you can see that we've got some inductors under here. Just looking at them I am a little bit worried about them because they do look just a little bit green, as though we could have some corrosion on there, and if any of these inductors are damaged that really could be game over. I can also see that the actual range selection switch, it's actually covered in kind of green corrosion, so all these switch contacts are going to need a good clean. Going back to our rectifier valve, the actual high tension supply here, it actually gets smoothed by two capacitors via this resistor, so we've actually got a CR smoothing arrangement. Now I can actually see that both of these capacitors have actually been replaced in the past. These aren't actually original, and looking at the values on them, these are both 8 microfarads. Now that's actually incorrect for this rectifier valve, because the actual rectifier valve states a maximum capacitance of 4 microfarads. Now you really don't want to put too big a capacitors on the output of a rectifier valve, because it does actually strain the rectifier valve and can shorten its life. So what we'll do is we'll probably go ahead and replace these with some modern 4 microfarad high voltage capacitors. We can see we've got two capacitors here. Now originally these would have been wax capacitors, but I can see that somebody in the past has gone ahead and replaced these with a more modern polyester alternative. But they haven't fared too well, because I can see that this one has got a great big crack down it and it's actually opening up. So although this is more modern than the original waxes, certainly we're going to have to change it out. Just looking at them, we've got, what's that? We've got a 0.05 microfarad at 600 volts, and I think that's a 0.03 microfarad again at 600 volts. So we need to change them. Our Taylor signal generator has a 400 Hz internal oscillator, and that oscillator can be used to produce an AF output, and it's also used to actually modulate the RF waveform, and it does that via this modulation transformer here. Now I can see that coming out of the modulation transformer we've got some very, very fine fragile wires, and again these were originally with silk covered. I can see that the silk has pretty much rotted away from these. I'm just hoping that these windings are intact. Now of course we have actually rewound small transformers like this in the past, but I would rather not do it if we have to, because it can end up being quite a lot of work. So fingers crossed our modulation transformer's okay. Maybe we should go away and just bell it out relatively quickly. At the bottom of the signal generator here we can see that we've got this square metal can. So what this actually is, it's a shielded attenuator box. So we've got actually a selector switch here, and what this actually does, it brings in various resistors, and it allows us to reduce the RF output power from the signal generator, which comes out of that connector there, so you can actually adjust it to the level that we want. Now they don't want that high RF energy, they don't want that being transmitted all around the internals, so they've actually put the attenuator here, they've put it in a screen metal box, and they've actually tried to seal the box by just soldering it here. So we're going to take a look in there, but before we do that of course we're going to have to remove this solder so we can get the lid off it. On the front of the signal generator we have a control here for adjusting the frequency, and what that does, it actually adjusts a variable capacitor. But I've never actually seen a drive quite like this, because this isn't actually a rubber band, it looks like a piece of steel here. So I can just twang it, so the drive is being transferred from the adjustment knob here to that variable capacitor using this steel band here. That's a little bit unusual, never seen one like that before. In preparation for applying mains power to the signal generator for the first time, I've gone ahead and I've reattached our plug, and I've also replaced that 13 amp fuse with a 1 amp fuse, which is going to be an awful lot safer. Now, before I power up any mains operated equipment, I do like to do a few tests first, especially a piece of equipment like this one that has a metal chassis. I also want to check that this transformer has got a good primary winding, because if this transformer's bad, it really is game over. So I think I'm going to start with that. So we've got our meter here. This is an insulation resistance meter, but at the moment I've got it set to the ohms range. So let's just see if we can see that primary resistance of our transformer. Now, I'm expecting something probably between 100 and 300 ohms. Not exactly sure. Let's find out. Okay, we've got nothing. Okay, I'm not going to panic at the moment, because hopefully we've got nothing because the piece of equipment is switched off, which it is. Let's switch it on. Okay, so we've got about 200 ohms there, 234 ohms to be precise. I'm not exactly sure what the meter reading should be, but we're in the ballpark. The next test that I'm going to do is for earth continuity. Now, because this piece of equipment does have a metal chassis, if we get a fault on it, it's quite likely that all this metalwork could become live. If I was to touch it, I'm going to get a nasty electric shock. So really, we want to make sure that the chassis itself is earthed. Now, of course, the chassis is earthed through the mains plug here, through this pin on the end of our plug. So we're just going to do a continuity reading here between the earth pin and various parts of the chassis, just to make sure it's got a good earth on it. So I'm going to start off by just getting a reading for the pin itself here. So we've got 1 ohm there, so it looks like the resistance in my leads here is about 1 ohm. Let's go to the actual incoming earth cable here where it's bolted to the chassis. Okay, still says 1 ohm, so we've got a nice low resistance. Let's try another piece of metal work. And again, 1 ohm. So that proves that this piece of equipment is satisfactorily earthed at the moment. And finally, the next test that I'm going to do is insulation resistance. And basically what I'm checking here is that none of the live parts are actually in contact with the chassis. So we have no leakage between the live and neutral and an earth. And the way we actually do that is I take my clip lead here of my insulation meter. I do have to just move the leads over to put this into the insulation range. And I'm going to do the test here at 250 volts, because I'm a little bit concerned about these microcapacitors in our filter. I don't want to put too much voltage across them, so I'm going to go to 250 volts on there. So these probes are now live. The first thing that I do is make sure the meter's working, so we should get so we're getting 0 ohms. Now I'm going to go between the live wire. We're getting 160 meg ohms and climbing. I'm going to go to the neutral wire. We've got 168, 170 meg ohms and climbing. So we've got no leakage between the live neutral and the earth pin. So in theory, the insulation on this transformer primary looks good, and we don't have any insulation breaking down. So having done that, we can probably go ahead and apply some power. As you can see on the bench, I've got my lamp limiter set up, and I've also got that plugged into one of these energy monitoring plugs, so that can show me both the voltage that we're applying and also, more importantly, measure the current, because if this thing has got a fault on it, it's probably going to draw more current than it should. Now, just looking at my mains voltage at the moment, it is actually particularly high today, so I'm actually measuring 253 volts, which is a little bit higher than I want, but I'm sure we'll be okay. Again, before proceeding with the lamp limiter, I'm going to remove this bulb because I think this one's about 200 watts. Again, this is only a small device. We don't need to supply so much current to it, so I'm going to put a 100 watt bulb in instead. And as we saw earlier, these actual main smoothing capacitors here, not only are they the wrong values, but they're in a really poor state. I can see that they've actually been leaking the electrolyte out, so I don't want these to explode because they probably will. So to stop that from happening, the first time we apply power, I'm going to go ahead, I'm going to remove the rectifier valve. So although our transformer will be producing a high HT AC output, we're not going to rectify that and apply any DC to the circuit until we've made a few more checks. So let's switch on for the first time. And immediately we have been rewarded by the actual equipment power indicator lamp illuminating. So yes, we've got 6.3 volts to the valve heaters. I can actually see the end of this valve here. The filament is starting to glow. So it looks like certainly we've got a good low tension winding here on our transformer. I can also see that the bulb on my lamp limiter is not actually glowing at all, which is a good sign, which actually means this thing is actually drawing very little current. That's also confirmed here by the actual wall wart energy monitor, because it says that we're drawing about 13 watts at the moment. So all that looks good. Let's just confirm what this low tension supply is. Okay, so the meter says it's about 6 volts, which is okay. So let's check our high tension supplies. Now the transformer arrangement on here, it's a centre tapped arrangement into what's a full wave rectifier. Now it's quite important that we actually measure the voltage on both sides of the centre tap for the HT supply, and the voltages really should be within a few volts of one another. If they're not in a few volts with one another, it's kind of indicating a fault with the secondary on the transformer. So let's just check that now. So we need to check pins 3 and 5 on this particular rectifier valve. So I'm going to put one lead on the chassis here and need to find pin 3. So 1, 2, there's pin 3. So we've got 171 volts on the first anode. Let's check the second anode. And about the same, 171, 172 volts AC. So that's good. Looks like we've got a good secondary and primary in our transformer. So that's nice to see. Snippy, snippy, snip, snip. I've swapped out both of the main smoothing capacitors here, and you can actually see that the two capacitors are actually joined by a resistor, a 10k resistor in this case. And this 10k resistor, it's part of what they would call a CR, a capacitor resistor smoothing arrangement. Now if I just actually put my meter across here, we can actually say that the indicated value on the ohms range, it's measuring about 14k, climbing towards 15. So I think that this resistor here has gone high in value, so I think we're going to change it out while we're here. Snippy snip snip. And now we've got one side out of circuit, let's just check it again. Yeah, it is high. So in the process of changing out these cracked polyester capacitors, which I think are something like C8 and C7, I also found that there is a resistor next to it, which should be about 30k. I think this resistor is R3, but again, having checked it, it does actually seem to have gone high in value, so it's actually measuring, yeah, closer to 40. So while we're in here, we may as well again change this out. And this is another modern component, or a relatively modern component, an Allen Bradley style resistor. So again, this had been changed out by the previous owner, but as you can see, it's gone high in value. I've gone ahead and I've changed out most of our passive components, and I'm taking the risk that this coil box here and the inductors are going to be good. And I think we've just got one more DC blocking capacitor, and that's actually hiding inside this shielded can. Now to get access to it, you can see that this can is actually been soldered together, so we've got the big soldering iron out, and I thought I'd bring you back because there's a really good chance I'm going to burn myself badly. It'd be a shame to miss that on camera, wouldn't it? So let's have a go. I think originally the RF output from the signal generator came via a 2-pin plug, but that's actually been replaced in the past with a more modern BNC, and I'm guessing at the same time somebody actually replaced the capacitor as well. So this is probably a relatively modern capacitor, but I can see, just looking inside it, I can see that it looks pretty kind of discoloured, so I'm not sure whether this is good or not. Seeing as we're actually in here and we've gone this far, let's change it out. So taking a close look at our DC blocking capacitor, it's actually a 10 nanofarad capacitor rated at 350 volts, but I can actually see that the package itself is kind of cracked and internally it's discoloured. So I'm glad that we went ahead and changed this out, because it looks as though there's something possibly not quite right with it. Our 10 nanofarad capacitor's actually reading closer to 35 nanofarad, so it's out by a factor of 3. Well, I don't see the point in chasing around dirty contacts, and certainly I can see a lot of them. So while this is open, let's give everything a good squirt of switch cleaner. Now unfortunately the worst set of switches are probably the most important, which are actually the frequency range selector here. I can actually see that all the contacts on it, they are absolutely green, and I'm hoping that the inductors themselves are in good order, because I can see a lot of that wiring is also green. So that's not great, is it? So all we can do is hope and give it a good spray. I think the time's come where we can replace our rectifier valve here and actually power the equipment up and see if we've got some high voltage DC. Let's go ahead and plug back in and switch on, and we've got our supply indicator lighting up. And we should get our high voltage, our HT, being developed across this resistor. So I think one side is probably straight from the rectifier and the other side of the resistor is the smooth side. So let's take a look at that. Let's give it just a few moments to warm up. So we can see that we've got 184 volts on one side of our resistor. Let's see what we've got on the other. And we've only got 106 on that side of the resistor. So across our smoothing resistor we are actually dropping 77 volts. This is a 10k resistor, so that means that we're passing about 8 milliamps through this resistor. Now 8 milliamps doesn't seem like a bad number, it seems in the ballpark, but we do seem to be dropping more voltage than I would expect across this resistor. Now I'm not dead sure about the value for this. Now the resistor that was in here previously was a 10k resistor, but the circuit diagram I think indicates it's something like a 5.6k, so it could be the wrong resistor. I'm not sure. Let's leave it as it is for now and we'll maybe come back and investigate further. Also think that just the all of the HT is probably just a little bit low, so it could just be that this rectifier valve is also just a little bit weak as well. That's something again I can check later. Hopefully we can just pick this up without electrocuting myself, and let's see if it's actually functioning. That's the test, isn't it? So I've got a dummy aerial here. I guess I'm going to stick this onto the RF output. Probably won't need an aerial, I'm sure it's radiating lots of RF anyway. And I've got a transistor radio here. What's that set to? That's set to about 1 megahertz. So as you can hear, we have actually got a tone, so we are working. But looking at the dial here, we should actually be on 1 megahertz, which I think would be there, and we're actually not. We're actually only at 900 kilohertz there, so I actually think maybe we're a little bit out of calibration. But one thing we can hear, let's turn the sound up again. Yeah, definitely low on frequency. We've got the modulation input turned on, so yeah, we can hear the modulation, probably around 400 Hertz. That's the modulation turned off. We should be just getting a dead carrier now. Can we hear that? Yeah, we are getting some quietening. So it looks like the carrier's working. Let's get a frequency counter and try some of the other ranges. I've got my old Tektronix TDS 2022B on the bench, and we're just feeding in an input from the signal generator. Now I've got the signal generator set to 100 kilohertz at the moment, so we're on our lowest range. We can actually see here that on the frequency readout that we're actually at 101 kilohertz, but really pretty close. And just taking a look at the sine wave, well, I can see some harmonic distortion. It is some way off a perfect sine wave. It's a little bit distorted at the top and the bottom, and it's got a slight bulge in it, but I really think that's probably to be expected from such a simple device of this, because it really isn't a very complicated signal generator. So let's try some of the other ranges. In fact, let's just try increasing the frequency. So this should go up to 300 kilohertz, so let's just do that. And this time we're about 11 kilohertz out. Let's try the 300 to 900 range. With the signal generator set to an output of 300 kHz, we're actually getting something just a little bit above that at 305. Let's turn it up to 900 now. And at 900 it's actually reading 927, so again a little bit out. It's reading on the high side, isn't it? So we're now on the range that covers between 900 kHz and 2.7 MHz. And we can see again at the lower end of the range we're at 900 kHz at the moment. We can see that we're just slightly high at around 910 kHz. Let's increase the frequency to the top end of the range. This should be about 2.5 MHz, actually reading 2.6. Let's move on to the next range, which is 2.7 to 8 MHz. So the amplitude has dropped off a little bit, but it is actually reading around 2.7 MHz. Let's go to the top end of the range, which will be 8 MHz. And this time it's reading just a little bit low at 7.5 MHz. And finally we've got the last range, which goes between 8 MHz and 23. So let's select that. So I'm on the 8 to 23 MHz range, and unfortunately we don't see a trace on the oscilloscope anymore, but if I actually increase the frequency just a little bit, it does appear that our oscillator does start working. So for some reason it doesn't work at the very lower end of this range, so maybe that takes a little bit of investigation. Now quite often when you get things like that, it can actually be the oscillator valve. It may be worth just changing that out, but in my experience if it's a weak oscillator valve it usually affects the top end of the frequency range rather than the lower. But it does work. Let me just turn the frequency up to, I don't know, let's just pick a number. So let's pick here, which is about 13 MHz, and I think we're indicating on the scope here about 13.2, so that's not particularly bad, is it? Is it going to go all the way up to 23? Not such a good sine wave anymore, but again, don't think it really matters for what this equipment's designed for. And the frequency is about 23.7 MHz, so again, a little bit high. Now of course it's not unexpected that after maybe 70 years this signal generator maybe does just need a little bit of calibration, so I'm going to look at that at a future time. And it could also be that we really haven't given this signal generator any time to warm up, so the frequency accuracy could improve because it's only been just switched on now. Maybe if it was left to warm up for an hour or two it might do a little bit better, because valve equipment does tend to drift, especially when it's cold like it is at the moment. It could be a little bit different when it's reinstalled in the original box where everything heats up a little bit more. To finish with today, let's turn on the 400 kHz modulation. Now we can see that the carrier is actually being modulated, more so at the bottom of the waveform than at the top. I suspect that this is probably normal for a signal generator of this type, because again these are relatively low specification, so the fact that it really isn't symmetrical, it doesn't make a huge difference. This piece of equipment would actually work for the purpose which it was intended for, which is probably just for radio alignment of fairly low end and domestic receivers. But I do think it probably is working good enough, or as well as can be expected. Well, I think that seems like a good place to finish for today, because certainly we do have our signal generator working, and I think what I will do is I'm going to take some time to cosmetically clean up the signal generator. I'm sure some of this bright work will polish up absolutely beautifully, and maybe we'll also have a go at calibrating it, see if we can actually improve the frequency reliability of it. If you want to see that in another video, leave it in the comments. But until then, bye bye for now. Bye bye.